Welcome to the Explainer. Today we're tackling a classic piece of physics magic that helps design everything from massive telescopes to the side view mirror on your car. Our goal today is to quickly demystify the geometric derivation of the spherical mirror formula. If you've ever wondered where this foundational optics equation actually comes from, well, you're in exactly the right place.
Okay, let's dive into this. Before we start building our proof, let's look right at our exact destination. The famous spherical mirror formula simply states that 1 over the focal length, f, equals 1 over the object distance, do, plus 1 over the image distance, di. By revealing this final formula right away, you know exactly what it is we're trying to reverse engineer here. Now, what's really interesting about this slide is the physical setup that makes it all possible. We've got our object, labeled AB, placed a very specific distance away. That's our DO. Light rays travel from the object, hit the mirror, and then reflect back to form an inverted image, A', B', located at distance DI. Honestly, this simple geometry is the entire playground for our derivation.
All right, section 1, our first set of triangles. This is where we'll start building our proof using similar triangles.
To unlock this formula, we're going to use the mathematical superpower of similar triangles. And instead of getting lost in a giant variable soup, let's just focus on the pure logic. Notice those two triangles formed by the light ray hitting the pole of the mirror, triangles A'PB' and APB. Because the angle of incidence perfectly equals the angle of reflection, and both triangles share a right angle, they are mathematically similar. That means the ratio of their heights, AB over A'B', is perfectly equal to the ratio of their base lengths, PB over PB'. And there we have it, our equation 1. Let's move to part 2 and see how this builds our second ratio. So we're just going to repeat that exact same process, but this time we're looking at the light ray passing right through the focal point, which creates triangles ABF and FPE. By applying that exact same rule of similar triangles and substituting our terms for the image height, we find another ratio. We get AB over A'B' equals BP minus FP, all divided by FP. And that right there gives us the final piece of our mathematical puzzle, equation 4. Section 3. Deriving the final equation. So, the crucial point is combining these ratios we just found.
And this brilliantly illustrates the real magic of this proof. We have two different equations that both equal the exact same height ratio. Since they equal the same thing, we just set them equal to each other. In step 1, we replace the line segments with our actual physics variables, object distance, image distance, and focal length. Then in step 2, a quick, simple cross multiplication flattens it out beautifully. Finally, in step 3, we divide both sides by the combined term DO, DI, and F. Everything just neatly cancels out, perfectly landing us right back at our starting formula. 1 over F equals 1 over DO plus 1 over DI.
We've successfully reverse engineered the formula using a concave mirror setup, which is awesome, but it leaves us with a pretty fascinating puzzle to ponder. How would this geometric derivation change if the mirror were convex instead of concave? Think about how those similar triangles would shift around. Thanks so much for joining me on this quick explainer of geometrical optics, and hey, keep exploring those angles.